started. Okay, welcome to physics for October the 6th. So before we get into the main stuff, let's talk through a couple logistical things. Do not forget that you have an assignment, which is to redo the test. Even those of you, even that one of you that got a perfect score, and that other one of you that missed a perfect score by only 1 point, okay, you need to redo the test as well. It counts for 52 points, which is 5 times as much as the regular homework assignment is worth. So don't forget to do that. It is due on Saturday at midnight, so you got plenty of time, but don't go putting it off thinking, well, I got time, I'll do it on Saturday. Not a good idea. So everybody needs to do that and figure out what you did wrong. And you can retake it multiple times if you want. And I've got Canvas set so that if you get one wrong, it'll tell you which one you got wrong. It won't tell you what the right answer is, but it'll tell you which problem you got wrong. And you can go back and you can do it as many times as you need until you get it perfect. Okay, let's see. Oh, another important thing. I am doing an experiment right now with the quiz. Last several weeks, people have told me that 5 minutes wasn't really enough time to do the quiz. They felt too rushed. They weren't able to get it done. And I hear you. So I'm going to give you 10 minutes on the quiz. But here's the thing. 10 minutes is just too much time during this face-to-face time that we have that some teachers call the synchronous time. I just can't spare 10 minutes. That's just too much time. So what I'm going to do is after we finish this face-to-face synchronous time, then during what they call the asynchronous time, okay, that's when you need to take the test, right? So as soon as you guys type "bye" into the chat box, then first thing you should do is you should take the quiz, okay? All right. With that being said, let's see. Let's review the homework. Let me share my screen with you. All right, so here is the homework from last assignment. If you have any questions, now's the time to ask. Remember that the questions to the odd number ones, I'm not putting them here because I've trusted you've already looked them up in the back of the book. No questions?
Could we talk about 4?
You bet. Number 4. Okay, so that's one where we've got a rope lifting a bucket at constant speed, and we're supposed to do a free body diagram. Okay. All right. So now free body diagram, that means that we need to draw the object of interest and the forces that are acting on the object of interest. All right, so let's say this is the bucket. Is it a bucket? Whatever it is, okay, a bucket. And it says it's being lifted at constant speed. Okay, so the object is right there. Anything that's in contact with the object, we don't draw that because we define our system to be only the object that we're interested in. Now, those objects that are in contact with the object of interest, they're probably exerting a force on it, and we definitely do need to catch the force in it. But we only draw the object that we are interested in studying. And I like to switch to a different color. So for the forces. All right, so we're going to have a downward force, which we're going to call the force of gravity, although later today I'm going to ask you to start calling it something different. You'll see in just a few minutes. And then if the bucket is being lifted upward, there must be an upward force, and so that's from the rope. Now here's the question. When I ask you this question on a test, which I probably will, okay, what I'm going to be looking for is to see if you've got the arrows the proper length. So if the thing is moving at constant speed, that means it is not accelerating. So that means that the downward force and the upward force are balanced. Okay, so that means that the force of the rope should be the same length as the force of gravity. Now I just hand sketched it, so they may not be exactly the same length, but I mean, to as close as I'm able to reasonably draw them, those two arrows should be the same length. Now, always there's a couple of students that say, well, wait a minute, if it's moving upward, shouldn't the upward force be greater than the downward force? Which is a logical question to ask. But the thing is that at the very beginning, in order to get the bucket moving, I will agree that for a brief second, the upward force did have to be greater than the downward force, because otherwise the bucket wouldn't have started moving. But once it starts moving, if it moves at constant speed, that means that the two forces are equal in length. Okay, so that's what I'll be looking for if I put this problem on a test, which I very well might. And then problem number 2 is one that I wanted to discuss. And it's pretty similar to this one. If you've got a skydiver, so let's draw the skydiver. So there is the skydiver minus arms and legs and head. Makes it easier to draw. And so I'm going to put the forces in a different color just because I like it. So when the skydiver first steps out of the helicopter or the balloon or the airplane or whatever, I like helicopter and balloon better, because if they step out of a moving airplane, then people think, well, don't we need to account for the sideways motion? And technically, yes, but I don't want to go there. So let's just assume that they're stepping out of a helicopter or a balloon. So when they first step out, let's look at the forces on them. Okay, so the force of gravity is going to be pulling down. Okay, that may not look like an FG, but it is. Let me try that again. Okay, the force of gravity. Okay, now when they first step out, they are not moving, so air resistance really isn't a factor. So you've got a downward force, and that's it. And so they're going to start accelerating downward, and they're going to move faster and faster and faster. And the faster they move, the more there's going to be air resistance. So at first, there's not very much air resistance. Then a little bit later, there gets to be more air resistance. And after not very long, they will be moving so fast that the upward force of the air resistance will be equal and opposite to the downward force of the gravity. And so it's like the picture we had over here. So we have a name for this. We call this terminal velocity. When the skydiver reaches terminal velocity, the downward force and the upward force will be the same. Now, some students say, well, does that mean they stop moving? No, it just means that they stop accelerating. So they will be moving at constant speed. And like I say, we have a name for that. We call that terminal velocity. Okay, any other questions? Not seeing any, not hearing any. All right.
I have a question.
Yeah.
It says not forces would be mass.
That's
Why,
right.
or inertia, or acceleration. Could you go over why those aren't forces?
Okay. All right. Let me stop sharing here. Okay, so I can understand why some people think that mass is kind of a force. Okay, so if this object has some mass, so I put it here on the table or wherever. Okay, so when I push on it, it pushes back, it resists. And the reason it resists is because it has mass. But if I'm not pushing on it, is it exerting a force? No, right? So mass, which is related to inertia, yeah, I can see why, you think, okay, I push on it, it pushes back, therefore it's a force, but no. The fact that it has mass, that is not by itself a force, because if I'm not pushing on it, it's not going to be pushing back. Therefore, you can have all the mass it wants, but then there's no forces, right? Same thing with acceleration. Acceleration is not a force. Acceleration is what happens because of an unbalanced force. Okay, so I don't know what more to say other than that.
Okay, thank you.
Okay, now 10 through 14, those were important ones that I thought we should discuss. Number 10, how could you feel the inertia of a pencil? Anybody have any suggestions? Now, I don't have any pencils handy, so we'll have to use a pen. How could I feel the inertia of this pen? Somebody unmute yourself and speak up.
If you stop it.
If I stop it, I'm not sure what you mean by that. I mean, if it was moving, oh, okay, maybe that's it. Okay, so if it's moving and it hits my hand, so boom, okay, I just felt it. Okay, if that's what you mean, okay, I can understand that. Okay, that'd be a good way to do it. Another thing I would recommend is let's take the pen and let's put it on a tabletop and let's flick it with our finger. Okay, so if I flick that thing hard enough, it's going to hurt my finger. I can feel the inertia, even though a pen doesn't have very much inertia. If I flick it hard enough, I want to get the thing moving. I want to get it accelerating really fast, I can hurt my finger. Now, how about the book? If I flick the book, oh yeah, I definitely hurt my finger, and the book doesn't even move as a result of that. Okay. Okay. 11 and 13 are ones that I want to discuss together. In problem number 11, we have an object that's being lifted at constant speed. So when we do the free body diagram for it, we need to make sure that the downward force of gravity and the upward force of whatever it is that's pulling it up, they must be the same length if it's moving at constant speed. Now, in problem number 13, it says that it's not moving at constant speed. In problem number 13, it says that you've got some object here, and it's moving upward, and it's being pulled upward, but it's decelerating, right? Yeah. Okay. So let's do the free body diagram. And let me switch to a different color because I like to do the forces in a different color than I do the objects. All right, so you're going to have the force of gravity pulling down. You've always got that if you're anywhere near a massive object like a planet. Okay, it's moving upward and it's being pulled upward, but it's slowing down. So that means that the downward force is greater than the upward force. So if I were to put this on a test, I would look to see that the force up is shorter, the arrow there is shorter than the one down. The length of the arrow is very important. Okay, when you guys take the quiz or the test, if I ask you to draw free body diagrams, I'm going to be looking to see if the length of the arrows is the appropriate amount. I'll look to see, if they're supposed to be equal, do they look equal? If one of them is supposed to be greater than the other one, does it look greater than the other one? So I'm going to be looking for that. And I think that's pretty much all I really want to talk about for 11 through 14, unless you have questions about them. Okay, so I'll give you one last chance to ask any questions you might have. Not seeing anything, not hearing anything. Okay, all right, let's move on then. Okay, so the plan for today is we are going to finish up chapter 4. There's one important concept in chapter 4 that we haven't yet discussed, and that's Newton's third law. But before we talk about Newton's third law, let's just take a minute and let's just make sure that we're comfortable with Newton's first 2 laws. Those are important. Okay, so let me see. Who should I pick on here? How about Mercedes? Would you please unmute yourself and tell us in your own words, what is Newton's first law? What does it say?
Sorry, 1 second. I don't remember. I used to have that memorized, but I've forgotten it.
Okay, but you do remember in junior high school, your junior high school teacher talked about it, right?
Yes.
Okay, all right. Kennedy, how about you? What is Newton's first law?
I don't remember.
Oh, 2 strikes. Okay, let's go for 3. All right, Julia, don't let me down here. Don't have 3 strikes and I'm out here. Julia.
An object in motion stays in motion. An object in rest stays in rest.
Okay, thank you very much. That's exactly right. Okay, so Newton's first law. If you have an object that's just sitting there not moving, all right, then it wants to stay there. It's, what we talked about the object, even if it's floating in outer space here, so it's weightless, it still has mass, right? And so if it's sitting there not moving, it's going to stay not moving unless I push on it. Only when I push on it with an unbalanced force will it start moving. And the more mass it has, the more it wants to stay at rest, unless it's moving. Now, once it does get moving, then the second part of Newton's first law says that once it's moving, it wants to continue moving. And there's one part that your junior high school teacher may have left out. And up until now, it hasn't been important, but starting next week, it's going to become important. This object that's moving wants to continue moving in a straight line. Remember that next week. For what you do in tonight's homework, it's not going to matter, but next week it's going to become very important. Not only does it want to keep moving, but it wants to keep moving in a straight line. And the more mass it has, the more it wants to keep moving in a straight line, the harder for it is for me to slow it down. Okay, that's Newton's first law. All right, how about, let's see, Darian, what is Newton's second law?
Newton's second law?
Yep.
I can't remember.
Oh no, are we gonna have to go through 3 strikes again here? Shauna, what is Newton's second law?
So the acceleration of the object is equal to like the forces, I believe, like the sum of the forces acting on the object. Yeah.
You're leaving one. You're so close. You're leaving out one thing. Okay, so the acceleration is equal to the sum of the forces that are acting on the object divided by, help me out here, Shauna. What's it divided by?
The mass.
The mass. Very good. Okay. So most people, when they think of Newton's second law, they think of F equals ma. That's probably the way that your junior high school teacher taught it to you. Okay. Now, here in senior high school, we recognize that there may be more than one object or more than one force acting on the object. So if this is my object, if I have a force pulling it this way and a force pulling it that way and a force pulling it this way, okay, I need to add up all of the forces. So I'm going to take this symbol right here, the Greek letter sigma, which means we're going to add them all up, okay? So this is the version of Newton's second law that most people recognize, but Shauna prefers to rearrange it. She wants to divide both sides by an m, okay? And so she comes up with this, which is completely valid. Absolutely nothing wrong with that. These two are exactly the same as each other, okay? So this equation is Newton's second law. All right, now, time for Newton's third law, which we haven't yet talked about, but I'm willing to bet a large sum of money that somebody out there knows what Newton's third law is. Anybody want to help us out? Don't make me lose my bet here. Somebody unmute yourself and tell us what is.
Action has an equal and opposite reaction.
That's very good. That's exactly it. Some people call it the action-reaction law, or you can word it the way that that AJ just did, or I'm sorry, the crew just did. Okay, so basically, if I have a wall here, and I stand here, and I'm pushing on the wall. Okay, so let me change to a different color. Right, so this is the force of me pushing on the wall. Well, the wall pushes back. So this is called the action force, the one that I'm doing. And then this is called the reaction force, the one that the wall is doing on me. And Newton's third law says that these forces always, always, always come in pairs. Newton says that it's impossible to have one force without having a reaction force. So let's see if he's true. Let's see if Newton's law is right. I don't know if I've told you this. I may have left this out. I have always had a standing agreement with my previous year students that if you can break the laws of physics, I'll give you an automatic A for the rest of the year, and you don't even need to come to class anymore. Okay, so that's the deal. Let's see if we can do that right now. Let's see if we can break Newton's third law. All right, so what I'm going to do is I'm going to have a tabletop. I'm going to have an object sitting on that tabletop. And now I'm going to switch to a different color because I want to always do my forces in different colors. You might think that that's not really important, but it really does help. You'd be surprised. Okay, so let's do a free body diagram for this object sitting on the tabletop. All right, so the first thing is we've got the force of gravity pulling it down. Okay, but it's not moving down, right? Because it's sitting on a tabletop and it's not moving down. So there must be some force that's balancing it. And so, well, that would be the force of the table pushing back on the object. Okay. So if the thing is not moving, that means this upward force and this downward force are equal and opposite to each other. So I propose to you guys that maybe the table force here must be the reaction force for this gravity force. So I'd like you guys to type in the chat box here with me. I want you to tell me, do you agree that with what I just said, or do you disagree? So if we say that the gravity force is the action force, okay, is the table force the reaction force? So I want everybody to type in either the word agree or disagree with that statement. Okay, I see a lot of agrees. Nobody wants to disagree? Okay, well, okay, if you guys agree with that, then I think maybe we just broke the laws of physics, and here is how we're going to do it. Okay, we've got this object that's sitting on the table, and so what I'm going to do is I'm going to take away the table. So that means that the force of the table is no longer there, but the force of gravity is still there. So, hey, I'm thinking we just broke the law of physics. We've got a force without a reaction force. That's a violation of Newton's third law. Does that mean we can all go home? Oh, wait a minute. We're already home, or at least I am, and I think most of you are. Okay. Why is this not a violation of Newton's third law? Anybody want to speak up? Where's the reaction force? Max, what do you think? What happened to the reaction force here? Because Newton's third law says there always has to be a reaction force. I don't see one. Earth calling Max.
I don't know.
Ah, okay. Anybody else? Luke? Let's see.
Would it be the mass of the object?
Nice try, but mass is not a force.
Oh, yeah.
All right, so think of it this way. Let me draw, here's the Earth, and here's the moon. Okay, so the gravity from, the Earth is going to be pulling the moon towards it. So kind of the same thing. Where's the reaction force? Well, the mass of the moon causes a force on the Earth. When the Earth pulls on the moon also pulls on the Earth. So if I've got this box over here that was sitting, oops, oh, I hate it when I do that. I try to draw and I forget that I'm still in erase mode, not draw mode. Okay, so if I've got this box right here that's sitting on the table, okay, gravity is pulling it down. So even when I take the table away, whoops, now I'm not in erase mode. Okay. So even when I take the table away, the force is still there. So what's happening then is that we've got the Earth down here and the box is pulling the Earth. So that's the reaction force right there. Okay. So unfortunately, so I'm really sorry, guys, I got bad news for you. We didn't violate the laws of physics. That means you can't have the year off. And by the way, if I'm the one that violates the law of physics, then I'm the one that gets the year off, not you guys. If you want to get the year off, you have to violate the laws of physics, not me. Okay, so that's pretty much all that we have that's new conceptually in the last half of chapter 4. But what we're going to do now is we're going to apply Newton's third law and also maybe let's do some problems where we have to apply Newton's first laws or second laws in ways that are a little bit more complex than we did in last night's homework. All right, so let's do a couple problems like you might see in tonight's homework. Let's start off with a problem that is clearly an application of Newton's third law. All right, so let's say that I've got the floor and I've got two boxes that are sitting on the floor, a big box and a smaller box. So I'm going to say the big box, I'm going to call it M1. The smaller box, I'm going to call it M2. And now in the real world, there is friction. And we don't yet know how to deal with friction, but you will learn very soon. Very soon we'll learn how to deal with friction, but we don't know it yet. So let's make the assumption that there's no friction. This is a perfectly slippery floor with no friction whatsoever, right? And so now what I'm going to do is I'm going to push on the box from the left side here, and this is the force of me pushing, okay? And so you're going to see that both blocks are going to move. So here's a question for you. Why does the block called M2 move? Because I'm not pushing on M2, I'm pushing on M1. So why is M2 going to move? Somebody unmute yourself and tell me.
Because the force of M1 pushes M2.
Exactly. Thank you. Yeah, so I'm pushing on M1, but M1 is going to be pushing on M2. So here we have a force right here, and I'm going to call that the force of M1 on M2. Now, Newton's third law says that there's going to be an equal and opposite reaction force. Okay, so that is going to be the force of M2 pushing on M1. And by the way, over here, there's going to be reaction force as well on the left side. When I push on M1, M1 is going to push back on me. So this is the force of M1 on me. All right. So we got a whole bunch of forces going on here. What you might see in the homework tonight or on a test is I might ask you to calculate what one of these forces is, one or more. But I would have to tell you some numbers in order for you to do that. So let's give you some numbers. Let's assume that I am pushing with a force of 28 newtons. Let's assume that M1 has a mass of 5.0 kilograms. Let's assume that M2 has a mass of 3.0 kilograms. Notice I want two sig figs here, okay? So what you might see in the homework or what you might see on a test is calculate what is the force of M1 on M2. Okay, so that is what I want to discover. All right. Anybody got an idea how you go about doing that? Well, I'll tell you what, I don't want to spend too much time. So in a normal world, in a normal pre-COVID world, what I would do is I would have one of you come up to the board and have you work your way through this. But because things take so darn much longer on line, I'm going to do it for you. So the first thing we want to do is draw a free body diagram. What we've got here might look like a free body diagram, but it's not a free body diagram because we got too much stuff on here. So let me suggest we do this in steps. So step one is let's find the acceleration of both blocks. And the way we're going to do that is we're going to define our system. Last time we talked about defining systems, but it may not have been obvious why it's important. But by being clever about how we define our systems, that can make an otherwise extremely difficult problem all of a sudden very easy. So what I'm going to do is I'm going to define my system to be both of the blocks together. Okay. And I am pushing on these blocks. So as far as I'm concerned, they might as well be one block because the M1 is going to push M2, so they're going to stay they're going to stay in contact with each other. So when I'm sitting over on the left side and I'm pushing on it, as far as I'm concerned, they might as well just be one block because they're going to move together. So I'm going to define them to be my system. Now, in a free body diagram, we only want to show the forces that are acting on the system. We do not want to include the forces that the system is exerting on me. So you see down here where I've got this force that M1 is exerting on me. I don't want that, because in a free body diagram, you only include the forces that are being exerted on the object of interest, okay? And these two forces in here, the force of M1 on M2 and M2 on M1, those are internal forces. I don't care about internal forces. I only care about forces that are acting on the system from external forces. Okay. Now, some of you might say, what about the force of gravity? You might say, oops, I hate it when I do that. I was in erase mode, not draw mode. Okay. All right. So some of you might say, we've got the force of gravity pulling down and the force of the floor pushing up, to which I would say you are correct, but those two are going to cancel each other out. And they're also acting vertically, and I'm interested in the horizontal direction, but they're going to cancel each other out. So just for simplicity's sake, I'm going to leave them out, even though technically you know, if you were thinking that I should put them in there, technically you're right. But if they cancel each other out, then I can ignore them. Okay, so I now have a free body diagram. Now I can use Newton's second law to figure out what the mass of the, or what the acceleration is. So Newton's second law says that F equals ma. Now, some of you are going to say, wait a minute, Mr. Hendricks, you left out the sigma, to which I would say you are correct. But in this case, there's only one force acting. So really, I don't really need the sigma here, but technically you are correct. So I'll go ahead and put it there. All right. So do we know what the force is? Yes. Do we know what the mass of the object of interest in? Now notice the mass is the two of these guys together, okay? So the mass is going to be 8 kilograms. So yes, we do know that. So could we now calculate the acceleration? Yes, we can. Okay, so if we divide both sides by m, so we get a equals, that's an a, that may not look like it, that's an a. Oops, there we go again, come on. All right. Okay, so A equals sigma F over M, which is 28 divided by, so 5 plus 3 is 8. So 28 divided by 8 is 3.5. So my acceleration is going to be 3.5, whatever units it is we use to measure acceleration in, which hopefully you guys remember is meters per second per second. So that's my acceleration, okay? All right, so now I'm gonna try and make a little room here so I can do some more drawing, okay? All right, so now you might say, okay, that's great, but that wasn't what I asked you to find. What I asked you to find was what is the force of mass 1 on mass 2. So you might think that I've just wasted my time here, but no, I haven't. So here's what I'm going to do. I'm going to redefine my system. So let me try to get rid of these dotted lines here without getting rid of other things. Okay, so I'm going to redefine my system now to have my system be only M2. So I'm going to draw a new set of dotted lines. So my system now is only M2. So now I can move on to step 2 is now I can find the force that I'm interested in. Okay. And so now I need a free body diagram. And so this force over here on the left side is not going to be part of my new free body diagram because that force is not acting on M2. I only want the forces that are acting on M2. Okay, well, what is it that's acting on to M2? The force that I'm interested in. It's the force that M1 is exerting on M2. That is the only force that's acting on M2. Now, some of you are going to say, well, wait a minute, you forgot about gravity and you forgot about the table. To which I'll say, yeah, they cancel each other out just like they did before. So I'm going to leave them out. Okay, so now I'm going to use Newton's second law again. So I'm going to do sigma F equals ma, but this time I've got a different system. My system is just this right here. So the force that I want is, the force that I put in here is in fact the force that we're interested in. So that's going to be the force of M1 pushing on the block. The mass is going to be only the mass of my system, which is not 8 kilograms anymore. It's only 3 kilograms. Okay. And the acceleration is going to be the same acceleration that we had before, because when we started in here, we didn't know what the acceleration of these blocks was. But thanks to what we did in step 1 here, we now know. Okay. So the force, we don't know that. That's what we're looking for. The mass, we do know that. And the acceleration, we didn't know before, but now thanks to step 1, we do. So now we are in business. So the mass is 3 kilograms, 3.0. The acceleration is 3.5 meters per second squared. So all we have to do is take 3.5 times 3, and that tells us that the force, the magnitude of this force here is 10.5, whatever units it is we use to measure force in, which in the metric system is newtons. Okay, so now we've got our answer here. So my screen here is getting so cluttered up. This is one real drawback of teaching over Zoom, is I really need to have more board space. But we now know what this force is. This force right here is 10.5 newtons. Okay, so bingo, we're done. So I'm pushing from the left here with the force of 28 newtons. 10.5 of that gets transferred over to mass M2, and then the remainder of it is all gets used up, overcoming the inertia of M1. All right, so does this make sense? So I'd need you to either type in the chat box or give me thumb up, thumb down, whatever. I prefer chat box actually, and if you want to type it in as a private message so that others don't see, that would be fine. So give me a yes or no. Yes means this makes sense, I got it. No means I'm not sure. Please go on. Okay, good. I see a few of you are being honest and saying mostly rather than saying absolutely yes. And some of you said, yeah, I think with practice I'll be able to get it. So, and I agree. That, yeah, after you've done a couple problems like this, hopefully it'll sink in. Okay, so that's how Newton's third law is going to be used in the homework or maybe on a test. Okay, now one person just sent me a private message saying that they don't understand why I only use the mass of M2. So thank you for asking that. That's really important. Let's go back to our drawing here, which actually this thing's so messy. Let's clean up. Let's start with the fresh drawing. Okay, so if we've got two boxes like this, okay, and they're in contact with each other, okay, if I am interested in the force that the M1 is exerting on M2, so this force right there, that's the thing that I am interested in, then what I need to do is I need to define my system in a different color here, okay? So I need to define my system so that my system is only the object that that force is acting on, okay? If this right here is the force that I want to find out, I have to draw my free body diagram so that the system, the object of interest, is the object that that force is acting on. And that force is only acting on M2. It's not acting on M1. It's coming from M1, but it's not acting on M1. So I hope that answers your question. Thank you for asking that. Okay, there's another type of problem that you're going to see in tonight's homework, and I guarantee you're going to see on a test. Okay, and it's an elevator problem. Elevator problems are classic physics problems. If you take any kind of a national standardized physics test, if you take the SAT subject exam in physics, or you take any kind of test, I guarantee there will be an elevator problem on the test. They are just such great examples of what you need to know in physics. So we're going to do an elevator problem. And what we're going to do is we're going to have an elevator, and we're going to put a scale on the floor of the elevator. This is like, a bathroom scale, like you stand on to weigh yourself. And we're going to have somebody who's in the elevator standing on the bathroom scale, and they are going to weigh themselves, and they're going to see how their weight changes as the elevator moves up and down and in between. Okay. So I'm sure that you guys have experienced this. I'm sure that you've noticed that you walk into an elevator, you push the button for what floor you want, the doors close, the elevator starts moving, and all of a sudden you feel heavier than you normally do. Okay. And then once the elevator reaches its normal traveling speed, then you feel that your normal weight. And then as the elevator approaches the floor that you want to stop at, so the elevator starts slowing down, you feel lighter than you normally do. All right. So what we're going to do here is we're going to actually stand on a bathroom scale as we ride an elevator. Okay. Now let's start off really simple. Let's assume that the elevator is at rest. And let's see what we weigh when the elevator's at rest. So the elevator's not moving. All right. So the object of interest here is going to be the person. And so I'm going to define my system so it is the person and only the person. Now I'm going to find out what are the forces that are acting on the person. So we got the force of gravity pulling down. Tell you what, let me switch that to a thicker one. Okay, so we got the force of gravity pulling down, and then we have the force of the scale holding us up, because we've got this gravity force pulling us down, but we're not moving down, we're sitting at rest. So that gravity force must be balanced by an equal and opposite scale, or equal and opposite force going up. What is it that's in contact with our feet? Well, it's the scale. So I'm going to say F scale. That's the force of the scale pushing us up. Okay, that scale is going to read what our weight is if the elevator is at rest. If the elevator is moving, then it's going to read different. Okay, so let me just do a little review here. How much does a person weigh if their mass is 50 kilograms? Okay, so I want you guys to type into the chat box, okay, and do it privately so that other people can't see. So I want you to tell me, what is the weight of a person if their mass is 50 kilograms? So everybody type into the chat box privately so other people can't see. What is the weight of a person whose mass is 50 kilograms? All right, I'm seeing one number. Okay, now somebody is saying that it depends on the force of gravity, and you are absolutely correct. Except for the second part of what you said is not correct. And I don't want to give it away by saying any more than that. Okay, I need to see a few more. Let me tell you that the numbers that I'm seeing are wrong. Okay, thank you. One person who I'm not going to name because I don't want to embarrass him, one person got it exactly right. Actually, I'm going to say it, Shay, because what you said is right. Okay, so Shay just said mass is not the same as weight. Actually, she worded it slightly differently, but okay. So most of the numbers that I saw, you said 50 kilograms was the weight. Okay, good. Zane, way to go, Zane. You got it right. Okay, so Shay is absolutely correct in saying that weight and mass are not the same thing. So the mass is 50 kilograms. That does not mean that the weight is 50 kilograms. We talked about this last time, but apparently it didn't sink in. So let's talk about it some more. Okay, let's say I've got a calculator here that has a mass of 1 kilogram, just to make things easy. Does that mean that this thing weighs 1 kilogram? Well, okay, what is the definition of weight? Weight is defined to be, now make sure you guys write this in your notes, this is really important. Weight is defined as how much force I have to exert in order to hold this thing up. So if I'm on the surface of the planet Earth and I have a 1 kilogram object, the force is not going to be 1 kilogram because a kilogram is not a unit of force. A kilogram is a unit of mass. Okay, the force is going to be something different. And I'll talk about in a minute just what it is. But what if I take this 1 kilogram calculator and I go to the moon? Is the force on the moon going to be the same as it was on the Earth? No, it's not, because the moon has less mass, therefore gravity attracts less. So the weight of this calculator on the moon is going to be different than the weight of this calculator on the Earth, but the mass is the same. And if I go into outer space, then this thing just floats it has no weight at all, but that doesn't mean it has mass. If this thing's floating in outer space and I come along and I flick it with my finger to try and get it moving, it's going to hurt my finger because it still has the same mass that it had before. So weight and mass are not the same. Now, the more mass something has, the more it's going to weigh. That's a true statement. But mass and weight are not the same. All right, so let's see if we can figure out what the weight of a 1 kilogram object is. Let's see, I hate to clear my drawing here, but let's do it. Okay. Let's say that I've got a 1 kilogram object. Okay, and gravity is pulling it down. So I got the force of gravity pulling it down. If I'm holding it in my hand, then the force of my hand, okay, is holding it up. This, by definition, is the weight of the object. Well, actually, let me take that back. That's actually not the definition of the weight of the object. The weight of the object is the force of gravity. This is the weight of the object, okay? And now in this case, if the object is at rest, then the force of my hand will be equal to the weight. But if we're in an elevator and we're accelerating, then it won't be the case. But let's keep it simple. Let's assume that we are at rest. So this right here is the weight. But if we're at rest, then this will be equal to the weight, okay? So how could I figure out how many newtons this is? Well, the way that I do it is I take my hand away. Let's, like we did before, when we had the object and it was sitting on a table, okay? If I take the table away, or in this case, I take my hand away, this thing is going to accelerate downward. And so we can use Newton's second law to figure out what it is. So we know that F equals ma. Now I'm leaving out the sigma because there's only one force here. So let's just leave it out. Okay. So on the surface of the planet Earth, if I drop an object and I measure its acceleration, what number am I going to get if I'm on the surface of the planet Earth? Okay. Somebody type into the chat box here. We talked about this last time. What number will I get if I'm on the surface of the planet Earth? 9.8. Okay. All right. Very good. Okay. And it doesn't matter if it's a 1 kilogram object or if it's a 10 kilogram object or if it's a 100 kilogram object. All objects accelerate downward at the same rate. Remember Galileo's experiment from the Leaning Tower of Pisa, which, by the way, most historians say he didn't really do it from the Leaning Tower of Pisa, but he did do it, where he dropped different objects and he found they all accelerate at the same rate. Okay, so Max, I do see your question, but let me hold off. I'll answer it later. Okay, so if we're on the surface of the planet Earth, we know the acceleration is 9.8 regardless of what the mass is. So if I'm holding a 1 kilogram object, then the force that I have to exert is going to be whatever 1 times 9.8 is. And so in that case, it's going to be 9.8. So the weight, let me try that again. Okay. So the weight of a 1 kilogram object is not 1 kilogram, is 9.8 newtons. What would the weight of a 2 kilogram object be? Well, it would be whatever twice 9.8 is, so it would be 19.6 newtons. What would the weight of a 10 kilogram object be? Well, it would be 10 times 9.8, so 98 newtons. Okay, so weight is always going to be whatever the mass is multiplied by 9.8 if you're on the surface of the planet Earth. Now, if you're on a different planet, this number is not going to be 9.8, it's going to be a different number. So this number is so important that we're going to give it its own special letter. We're going to call it G. Okay, so the weight of an object is not M. The weight of the object is M times G, which on the surface of the planet Earth would be M times 9.8. All right, so now let me go back to our elevators problem here. So here's the elevator. Here is the bathroom scale. Here is the person standing on the bathroom scale. Let's do a free body diagram in a different color, and I'm going to make my lines thicker. So we've got the force of gravity pulling down. This force of gravity is defined as the weight. Okay, and now hopefully you guys recognize that weight is always going to be equal to M times G. Okay, and so what I recommend that you guys do from today forward is whenever you hear me say force of gravity, I want you to automatically think in your brain mg. So when I say force of gravity, you say mg. Now, if I say acceleration due to gravity, that's just g by itself. But if I say the force of gravity, that's going to be mg. So just get in the habit of thinking force of gravity is mg. And tell you what I'm going to do is I'm going to say from now on, instead of calling this thing down here, instead of calling it FG, I'm just going to start calling it mg. Okay. So whenever I draw force of gravity, I'm just going to call it mg. And I want you guys to do the same thing. So let's not call it force of gravity anymore. Let's just call it mg. Okay, now, if the elevator is at rest, then the upward force, which is the force that the scale is going to read, will be equal to the weight of the object, which will be equal to mg, but only if the elevator is at rest. If the elevator is not at rest, then it will not be the case. So how could we calculate what it would be if the elevator is moving? Well, we use Newton's second law. We say sigma F equals ma. Okay. Now, actually, let's do the math here with the elevators at rest. So sigma F, what that means is, let's look at our free body diagram. Let's look at all the forces. So we've got this force right here, which we're going to call mg. We're not going to call it fg. We're going to call it mg, and it's going down. So I got negative mg. That's one of the forces. Remember, sigma means add them all up, right? Okay, so that means we have to include all of the forces. And so we've got the force of the scale going up. And since it's up, it goes in with the positive sign because I'm defining my plus direction up. So negative mg plus the force of the scale equals ma. Now, if the elevator is at rest, then a equals 0 and m times 0 is 0. So then all of this then equals 0. So negative mg plus fs equals 0. So if we add an mg to both sides, then we get fs equals mg, which most of you are going to say, well, duh, we already knew that. Obviously, the upward force has to equal the downward force if the elevator is at rest. But what if the elevator is not at rest? Okay. What if you've got your bathroom scale? Here's your person. Let's do a free body diagram. We've got the force of gravity going down, which we're going to start calling mg now. We've got the force of the scale going up. Notice that I made the force of the scale longer than I made the force of gravity, because I'm going to assume now that the elevator is accelerating upward. Okay. And let's put a number on it. Let's say it's accelerating at a rate of 1.5 meters per second per second. So I want to know, what is the force of the scale going to read? Because I know it's not going to be equal to mg anymore. It's going to be more. So how could I do it? Well, go back to Newton's second law. Sigma F equals ma. So wherever we see a sigma F, we're going to replace it with the forces. So we've got the upward force, which is going to be the force of the scale, minus the downward force, which is going to be mg, and that equals ma. Now, last time we did this, we said that a was 0, but now it's not 0 anymore. The elevator is now accelerating. So this equation here can be used to tell us what we want to know. Okay, so let's add an mg to each side. And so what we're going to be left with is Fs equals mg plus ma. So this equation right here can solve all of our elevator problems. So let's put in some numbers. Let's assume the mass of the person is 50 kilograms. Let's assume g is, of course, 9.8 because we're on the surface of the planet Earth. I've already told you that a was 1.5, okay? So the force of the scale then is going to equal 50 times 9.8 plus 50 times 1.5, right? So what does that equal? Well, 50 times 9.8 plus 50 times 1.5. So I get 565 newtons. So the force of the scale here, let me write it in here. So the force of the scale is going to be 565 newtons if the elevator is accelerating upward at 1.5, okay? What if the elevator is at rest? We never calculated what it was when it would be at rest. If the elevator is at rest, then the acceleration is 0, so we don't have that 50 times 1.5. All we have is this. So if the elevator is at rest, then it's 50 times 9.8, which is 490. Okay. So when you stand on a bathroom scale, that bathroom scale, if it reads newtons like a bathroom scale really should, you should weigh 490 when you're at rest. When the elevator is accelerating upward, you're going to weigh more. If it's accelerating at 1.5 meters per second, you're going to weigh 565 newtons. Okay. So does that make sense? Let me check the chat box here. My chat box went away. Okay. So I need you to type in the chat box yes or no, where yes means it makes sense, no means it does not. And you can type it in privately if you want. Okay, and I see some people are saying mostly yeah, or yes, sort of, or yeah, but I could use more practice. Okay, good. All right. Okay, good. Now let me just answer Max's question real quick, and then I'm going to turn you loose. Max asked me a question. I don't remember if he asked it privately or publicly, so you may not have seen his question. He says, how is a Newton defined? Well, a Newton is defined from Newton's second law. So if we've got F equals ma, Okay, a Newton is defined such that if it is the amount of force that's needed, so that if you were to take a mass of 1 kilogram and you were to accelerate it with an acceleration of 1 meter per second squared, 1 Newton is how much force would do the job. That is how the Newton is defined. All right. Okay. So I realize that's a lot, and you're going to need some time to think about it. This is not something that for most students makes sense the first time you hear it. You got to sit down, you got to do some problems. So in your homework tonight, there's a homework problem, or there's an elevator problem or two. In the textbook, there's an elevator problem. I highly, highly, highly recommend that before you do the homework, look through the textbook, see that elevator problem that they do in the textbook, and just work through it. See how they do that elevator problem in the textbook. That highly, highly, highly recommend that you do that. Okay, so let me just tell you what the homework is here. Let me share my screen. You could, of course, just look on Canvas because it is on Canvas. All right. Whoops, why did it do that? Okay, there we go. Okay, so here is the homework. Remember, take the quiz. So right now, I'm going to end the live part of our class. That does not mean class is over. We still have some time left in class. Take today's quiz. It is now unlocked. So do that and then get working on the homework. So before I end the class here, tell you what I'm going to do. I'm going to stop the recording. So that way, if any of you had any questions that you didn't want to ask because you say, well, it's being recorded and I don't want to embarrass myself, I'm going to stop the recording and then you can ask your question.